Hello everyone, this is video 14.5 on similarity. Um, we'll look at how we've sort of introduced this topic a couple of slides ago. It's very related to congruency, but a different idea. But you may want to go back and look at the triangle congruency criteria just as a little refresher before we get going. So just a little suggestion there. All right, so let's get started. Okay, so if we're going to be talking about similarity, a good place to start would be to define what similarity means. And we're going to see in this video a couple different ways of thinking about uh, how to define, how to observe, how to recognize similarity. So we're going to start off by looking at this idea of a constant proportion. So in order to talk about this idea of a constant proportion, though, we need to talk about this idea of corresponding. Corresponding parts we've kind of alluded to in the past, but just as a reminder, we want parts that are in the same place relative to the other components of the figure. So if we look at this 6 and this 12, now they're both between the 1 angle and the 3 angle. And so they are corresponding parts. Now, you might think, well, they're also corresponding because they're both over here on the right side of the triangle. And unfortunately, we can't always go by that because I could take this triangle on the right and reflect it or rotate it, move it all around, and then that side DF wouldn't be on the right side of the triangle. So we can't always go by where it is in the figure, the way that it's drawn, but we can always go by where it is relative to these components. Now, we can tell where a side is relative to where it is the angles. We can tell where the angles are relative to where they are the sides. So, for example, this angle 3 we know is between the shortest side and the longest side. And if we look over here, this angle 3 is also between the shortest side and the longest side. So we can tell where these things are, even if we rotate and flip and do all kinds of craziness with it, we can tell where the pieces are. So this is what we mean by corresponding. The same thing we can do here with the 9. We know that it corresponds to the 18, long side to long side, short side to short side. Now, if I set up my proportion, I'm going to make a decision here. I'm going to compare the big triangle to the little triangle. Now, I'm doing this just so I know that I'm going to be consistent. So I'm going to look at these corresponding sides here. So in the big triangle, I got the 12, and I want the ratio of that to the little triangle corresponding side, which is the 6. So I'm comparing 12 to 6. Those are the corresponding shapes. Now, I want to do the same thing with another pair of corresponding parts. And so I got my 12 and my 9. I'm sorry, my 18 and my 9. And so this constant proportion means that this proportion here should hold. And we see that it does because both of these are equal to 2 to 1. Now, I'm not going to go through it, but if I were to look at this third side, this 16 to 8, the middle side, it will hold in this proportion as well. And so again, is what we mean by this constant proportion. No matter which ratio that I get from corresponding parts, that ratio should always fit into this proportion. They should all be equal to each other. This is what we mean by a constant proportion. Now, this is the same thing as the scale factor. The scale factor is this ratio that I get in comparing these two objects. And so you can see that going from the little one to the big one, to the little triangle to the big triangle, that I'm multiplying everything by 2. So if I'm looking at these corresponding sides, the 8 times 2 gives me 16, the 9 times 2 gives me 18, so on, so on, so on. I do want to point out, though, that if I draw this arrow going the other way, if I were to go from the big triangle to the little triangle, now my scale factor changes and becomes 1/2, because now I'm taking these sides and I'm multiplying them by 1/2 in order to get the smaller triangle sides. So the scale factor is going to be relative to sort of like which direction you're going. Are you making it bigger, in which case the scale factor is going to be greater than 1, or am I making it smaller, in which case the scale factor will be between 0 and 1. So if we're told that shapes are similar and we have at least one pair of corresponding sides, then we can find the scale factor and we can find missing sides if we have the length of one side in one shape, but not the length in the other shape, the corresponding length in the other shape. This figure is drawn in a really nice way because everything's oriented so that the corresponding sides are oriented the same way. And so we can see that this is my middle side, and so they're both the vertical ones. These are my short sides. They're both the horizontal ones. And then we've got our hypotenuse, which is going at this nice up to the right angle. Now I can see that I've got my 12 and my 6, so I have a pair. I've got a pair of sides here, and so I can determine my scale factor. To go from 6 to 12, I know that I'm multiplying by a half, or if I'm going from the small triangle to the big triangle, I know I'm multiplying by 2. So the scale factor is the same scale factor as the previous problem. Well, I'm going to use the scale factor in a slightly different way. So now I'm going to use it to find these missing sides. So I would like to know how long this side is in the large triangle. Well, I don't know how long it is, but I know how long the corresponding side is, and I know what the scale factor is moving in that direction. So I know that this side now is going to be 2.5 times 2, and that gives me 5 centimeters. The same thing is going to be true over here. I got this 13 centimeters. I know the scale factor going to the small triangle is 1/2, so I know that this side is 6.5. So I can use this similarity, the fact that we have similarity, and I know the scale factor, and I know where the corresponding sides are, I can find missing side lengths. This is a really common problem to solve in similarity. So the other way to think about scale factor is going to be not comparing a shape to another shape, but comparing a shape to itself. And for this, I'm going to use this rectangle. Or this pair of rectangles rather. And these rectangles here, if I look at this one, then I'm going to make a ratio of the long side to the short side. And so I know my long side is 2 centimeters, my short side is 1 centimeter, and so I've got this ratio now of 2 to 1, long side to short side. Now, every rectangle that's similar to this rectangle has to have this internal scale factor that matches 2 to 1. And so if that it holds for any other rectangle, be it bigger or smaller, then I know it is similar to this rectangle. Now, the external scale factor that we looked at a moment ago is still going to hold, but the confusing part is that it's going to be a different scale factor. Now, to illustrate this, I'm actually going to change this problem, and I'm going to make this 4 into a 6. And this will help sort of like make clear what I'm talking about with these two scale factors. So if I want to find this short side over here, again, I know that my long side to short side ratio is 2 to 1. So this is my long side. That means my short side here has to be 3 centimeters. So again, my internal scale factor is 2 to 1 long side to short side. But if I look at my external scale factor, and that's comparing shape to shape, then I can see that the corresponding sides are actually 3 to 1. So this is the part that gets a little bit confusing. You could have somebody say, well, I see the scale factor as 2 to 1. Another person can say, I see the scale factor as 3 to 1. And they're both correct because they're talking about different scale factors. So we need to be really specific. Am I talking about the scale factor that's within the shape, the internal scale factor, or am I talking about the scale factor between the shapes, which is my external scale factor? Both of these ideas work, right? We just have to be very clear and very specific about which way we're thinking about scale factor. So for your checkpoint problem, I've got a figure here, and we can see that PQ is parallel to ST. And so I'll give you a little bit of a hint here. We know by vertical angles that this angle is the same as this angle. But of the other 4 angles, how are they going to be congruent? You may need to look back when we talked about parallel lines. How can we figure out which angles are congruent? We can tell that these are not isosceles triangles because we've got a 5 and a 6 here. So we can see that they're not, and there's a little happy little face there. We can see that they're not isosceles triangles, and so the sides are differently, and so the base angles are going to be different measures. So figure out how these two triangles are going to be similar, and then see if you can figure out the length of x and y. You'll need to find the scale factor as well. So I'll leave this problem with you. If you have any questions about this problem or anything else from this section, as always, bring your questions to class and we'll get them answered. All right, thanks.